Yes.
All right. So I said magnets or magnetic materials are three elements: iron, cobalt, and nickel. Of course, you can add steel, which is obviously not an element because it's an alloy of iron and carbon. These are the only materials that can be attracted to a magnet. I hope you know.
Yeah.
Copper cannot, aluminum and the rest of them cannot be attracted to a magnet. Okay, so having said that, the materials that contain iron in them are called ferrous metals. So they are also magnetic materials because they can be attracted to a magnet. Now, non-ferrous metals do not contain iron. Yes, so the next is magnetic field. Magnetic field is basically the region around a magnet where the magnetic force can be felt. I will explain this when we get to the next page. The region around a magnet where a magnetic force can be felt. Can you go to the next page? Okay, so this is a magnetic field. The area around a magnet, the area around a magnet where the magnetic force can be felt. You know, it is only when you come into the magnetic field that you can experience the magnetic force. You can think of it as the area around where you have your magnet, where when you bring a piece of iron, for instance, it can be attracted to the magnet. Outside the magnetic field, the magnetic force cannot be felt. I think that's clear. Now we represent magnetic field with lines called magnetic lines of forces. So these are imaginary lines used to represent magnetic field, and these lines run from north to the south pole. Magnetic lines of forces run from north to the south pole. Can you go to the previous page? I want to talk about magnetic lines of forces. So you go to the next page, you will see how the arrows are pointing. It will come out of the north and run towards the south. You can see it on the next page. Magnetic lines of forces run from north to south. So the arrows point out of the north towards the south. Okay. Now the magnetic strength or the strength of the magnet is greatest or greater where the magnetic lines are closer to each other. Look at these magnetic lines. Around which area are the lines closer to each other? Did you get my question?
Where the north and south is.
Yes, so around the poles. The lines are closer to each other around the poles. So it means the strength.
Isn't it greater where the north and south is?
Exactly, where the north and south, where the north pole and the south pole are. So the magnetic strength is greater at the north pole and the south pole compared to every other place between the north pole and the south pole, because the magnetic lines are closer here, closer at the poles. If you check the distance between the magnetic lines, the distance here compared to the distance at the poles, the distance at the poles are shorter, so they are closer at the poles. I think that's clear. Of course, when you move further away from the magnet, the strength decreases. Let's look at the laws of magnetism. Obviously, we know this popular law: like poles attract, or like poles repel, actually.
Yeah.
Unlike poles attract. Like poles repel, for instance, north and north will repel. Also south and south will repel. unlike poles attract, like north and south. So like poles are like north and north will repel. And also south and south will repel. You know, we push away from each other. But when you have north and south, they will attract. That's unlike poles. Did you get that? Okay, the next page. The Earth's magnetic field. You know, the Earth behaves as if it has a large bar magnet in its center. How do we know? How do we know that? If you suspend a piece of a bar magnet by means of a string, can you see this diagram the string? If this bar magnet is suspended by means of a string, and then it settles, it's suspended horizontally. What I actually drew was like, so it's suspended horizontally, you know, and then if it settles, the north pole of the bar magnet will always point to the geographical north of the Earth. Why does that always happen? Because the Earth itself has a magnetic field, and the south pole of the magnetic field of the Earth is in the geographical north, while the north pole of the magnetic field of the Earth is in the geographical south. I said the Earth has its own magnetic field. The Earth has its own magnetic field. The south pole of the Earth's magnetic field is in the geographical north. The north pole of the Earth's magnetic field is in the geographical south. So when you suspend a bar magnet, the north pole
What do you mean by suspend?
Okay, just like you attach it to a string. Can you see my hand?
Yeah.
Like I'm holding it by means of a string, and it is held horizontally like this. You know, if it is suspended, it will swing, and then eventually stabilize. It will swing for a while and then settles, isn't it? Once it stabilizes, the north pole of that magnet will definitely point to the geographical north. The geographical north. Why? Because it is being attracted to the south pole of the Earth's magnetic field. Did you get that? Or I should say that again?
Say it again, please.
Yes, please. Okay. I said the Earth behaves as if it has a large bar magnet in its center. This bar magnet I have here, the bar magnet, the imaginary bar magnet of the Earth, has its south pole facing the geographical north of the Earth. You do geography. Can you mention some countries in the geographical north? Yeah. Any country in the geographical north, yes. Geography has come to play here.
No, I can't.
Of course, there are many countries in the geographical north. UK is in the geographical north. I mean, in the northern hemisphere. UK is in the northern hemisphere. You have Canada. You have, you know, Russia and the rest of them. They are all in the northern hemisphere. Then when you come to the southern hemisphere, that's where you have countries like Australia, South Africa, New Zealand, South America, and so on.
Yeah.
You know, West Africa is around the equator. That's at the center of the earth.
Yeah.
So I said the magnetic field of the earth, the magnet of the earth itself, has its south pole facing the geographical north, while its north pole is facing the geographical south. That is why if a bar magnet, another bar magnet, is suspended like I demonstrated, you suspend it with a string such that it swings by itself and then settles. Once it settles, the north pole of that bar magnet will point in this direction I showed here. How is this north pole pointing? Towards which side?
South.
What do you mean? South of what? Do you mean towards the south pole of the Earth's magnetic field?
Yeah.
Which is in where?
The southern hemisphere.
Where the south pole of the Earth's magnetic field is in what direction?
South.
I'm cycling it. It's in the geographical north. In the north pole, in the geographical north of the Earth, is where you have the south pole of the Earth's magnet. Can you see this bar magnet inside the Earth?
Yeah.
Did you see that its south pole is actually in the geographical north of the Earth? That's what this diagram is showing.
Yeah.
The north pole of the Earth's magnetic field is in what direction? The north pole of the Earth's magnetic field. Please, when I say the Earth's magnetic field, is this rectangle inside the Earth that you should be looking at? The rectangle inside the Earth, which represents the Earth's magnetic field. Look at this rectangle.
Yeah.
The north pole of the Earth's magnetic field is in what direction?
North.
It's in the geographical south. Should I redraw this? Okay, let me know if what I've just drew here has shown at your end. I'm watching to see when it shows. Yeah, it has shown.
Yes.
That's a very bad diagram of the Earth, so you permit me to use this. So, my geography student, this is the geographical north of the Earth.
Yeah.
Is the geographical north, while this side is the geographical south. Right?
Yeah.
Okay. I said the Earth behaves as if it has a large bar magnet in its center. This is this bar magnet in the center of the Earth. The bar magnet in the center of the Earth has its north pole here, and its south pole here.
Yeah.
So the north pole is where?
Where the north pole is south.
The north pole is in what? The north pole of the Earth's magnetic field is in where? In what part? Geographical south.
South.
Why the south pole of the Earth's magnetic field is in where? In what direction?
Geographical north.
Geographical north. Okay. Now, I said if you suspend a bar magnet, this is maybe a ceiling or any surface, you're hanging it, and then you use a string to suspend the bar magnet like this, so that is it swings and stabilizes. Once it stabilizes, I told you this very bar magnet will always behave like this. See its north and see its south, and tell me which direction is this north pole of this bar magnet pointing towards.
The geographical north.
Where you have what?
The south.
Of the Earth's magnetic field, where you have the south pole of the Earth's magnetic field. So, do you know why the north pole of this magnet is pointing in this direction?
Because the north pole is attracted to the south pole.
Interesting, because opposite poles attract. So, the north pole of this bar magnet is attracted to the south pole of the Earth's magnetic field. Is that clear?
Yeah.
This is actually how we tell directions. In fact, this is the principle of operation of a magnetic compass. You know, we use a compass to tell directions, isn't it?
Yeah.
In fact, a compass itself is a small magnet that is resting on a pivot. Just like I'm hanging this bar magnet on a string, with a string, the compass rests on a pivot so that it can move freely. It is being pulled by the magnetic field of the Earth. So everywhere the compass will be facing, the north pole of the compass will be attracted to the south pole of the magnetic field of the Earth. So, why does the Earth behave as if it has a bar magnet? Because the core of the Earth contains magnetic materials. All of these things are in the... in fact, once I finish one, I will go back to your specification and tick what we've done so far. The core of the Earth contains magnetic materials like iron, nickel, and cobalt. You know, the Earth consists of the central part, which we call the core, which is liquid. I hope you know.
Yeah.
And then the mantle before you get to the upper layers where you have the earth crust. Am I speaking in the language you can understand, dear geography student?
Yes.
Okay. Yeah. You see how they are all meeting themselves now. So in the core of the earth, you have magnetic materials. In fact, the core of the earth contains iron and nickel, and it's in liquid form or some semi-liquid, and because of that, there's a magnetic field created around the earth itself. The earth itself has a magnetic field around it. As a matter of fact, the shape of the magnetic field of the earth is like the shape around a bar magnet. Go to page 2 of 20. Beautiful. This is the shape of the magnetic field around a bar magnet. And I did tell you, if you remember, that go to page 1. Let me do a very quick overview. Page 1. I told you that the magnetic field is just the area or the region around a magnet where the magnetic force can be felt, or where the magnetic force acts. We represent magnetic field using lines we call magnetic lines of forces. These are imaginary lines, that run from the north pole to the south pole. Go back to page 2, because this is important. I need to emphasize it. These lines, the arrows must point out of the north and point towards the south. Take note of that. Always pointing out of the north towards the south, because magnetic lines of forces run from the north pole to the south pole. Is that clear?
Yeah.
And I also told you that the magnetic strength is greater where the magnetic lines are closer to each other. And you can see that the lines are closer to each other at the poles. That's the poles of the magnet. Elsewhere, in between the poles, the lines are further away from each other. So the strength of the magnet is greatest at the poles where the magnetic lines are closer to each other. And of course, we talked about the fact that like poles will repel, like north and south and south will all repel, but unlike poles will attract. And of course, when you move further away from a magnet, this magnetic force becomes weaker. It doesn't pull as much as you will experience the pull if you were closer to the magnet. Isn't that's simplistic enough, isn't it?
Yeah.
And don't forget that on page 1 again, you need to look at it, because I was just talking about why the earth behaves as if it has a magnet. Go to page 1 again.
On page 1.
Yes, page 1 of 20. Yes, you're on page 1. There are materials that can be attracted to a magnet, and we call those materials magnetic materials. There are only 3 elements: iron, cobalt, and nickel. Of course, you can add steel as a material, because steel is an alloy of iron and cobalt, and carbon rather, with some other elements depending on the quality of steel you want. So ferrous metals contain iron, so they are usually magnetic because they have iron in them. Example, steel. Non-ferrous metals do not contain iron. Okay, so we said all that, and you on page 3 again. So you meet me on page 3. On page 3 again,
Yeah.
I want to draw your attention to the fact that what is responsible for the magnetic field of the earth is because of the presence of magnetic materials like iron and nickel at the core of the earth. The center of the earth, you find magnetic materials, iron and nickel. So they created the magnetic field that we have around the earth. Okay, so we've talked about that. Look at the shape of the magnetic field around the earth. Can you see this magnetic field around the earth?
Yeah.
It's the same shape as the one around a bar magnet that you find on page 2. They have the same shape. That's why we say the earth behaves as if it has a large bar magnet in its center. I hope this is getting clearer.
Yeah.
Interesting. All right, this is beautiful. So if you were to draw the magnetic field of the earth, you need to draw lines that will look the same way as the one around the bar magnet. And remember, the arrows must point out of the north pole of the magnetic field of the earth towards the south pole. So it will be coming out of the north and be entering into the south pole. So the arrows must be correctly indicated or shown. One more time, where is the north pole of the magnetic field of the earth? In which side of the hemisphere is the north pole of the magnetic field of the earth?
It's in the north pole magnetic field of Earth. It's in the geographical south.
Yes, it's in the geographical south, around where you have Australia and what have you. While the south pole of the magnetic field of the earth is in the geographical north.
Yeah.
Okay. Cool. Thank God that the earth has a magnetic field. Otherwise, it would be difficult to tell directions. You can imagine if you are in a deep blue sea where there's no other thing you're seeing around you. The only way you can tell the direction of your movement is with a compass.
Yeah.
And of course, that's what makes flying, air flight and all that possible, because with a compass, or even a navigation and all that, you need to use a compass. So let's move on. Very quickly, go to the next page. We'll be fast about it. What is responsible for the magnet in an object? An object itself has tiny magnetic materials we call domains, magnetic domains. See these red lines that are scattered. They are pointing in diverse directions. Can you see the red lines whose arrows are pointing in several directions? Okay, that's how the magnetic materials in every object is originally. So all matter, that includes air, gas, anything that is a matter. You know, a matter is anything that has mass or weight and occupies space. All matter contains tiny magnetic domains that are usually not arranged. Did you see that?
Yeah.
Now, to make a matter to become a magnet, you need to arrange or line up those magnetic domains. Like in this case, they are not lined up, they are scattered. I'm talking about the red one, the red arrows. The yellow arrows are showing when they are now arranged. Just like the red one on the right hand side, also showing where they are arranged. So any material that you can arrange the domains like this will become a magnetic material. So only iron, cobalt, and nickel, of all elements in the universe or in the earth as we know, only iron, cobalt, and nickel can have their magnetic domains rearranged. All other ones will not be rearranged. That's why only iron, cobalt, and nickel can be attracted to a magnet, because their magnetic domains can be rearranged to, align themselves in one particular direction. Is that clear?
Yeah.
In fact, when they are arranged, like in this case, here becomes the North Pole and here becomes the South Pole. Let's move on. Let's move on. We need to get it faster. So this is basically telling you how we can make something a magnet. One method is stroking. Stroking is you get a bar magnet, you begin to look at the way I'm moving. I need to quickly show you this. You see this thing I'm tracing here? Can you see it at the end?
Yeah, I see it.
That's a bar magnet. Now, if you're holding this bar magnet, short bar magnet, close to an iron bar, for instance, God have mercy. Okay, you're holding it close to an iron bar. And then you are moving it in this direction as shown. You know, you move it and back. What it will do will be to rearrange those tiny magnetic domains inside the bar magnet. So all of them will now align, like as you're seeing in this yellow line. Once they can align, the material has become a magnet. This is one way of making a magnet. So you can make a magnet by stroking. Stroking is what I just described here. Get a bar magnet and move it in this way such that the domains, initially scattered domains, are aligned to be all point in the same direction, so that you can have a definite North Pole and a definite South Pole, and not all of them cancelling out each other. There's another way that can be done, magnetic induction and all that, and so many other methods.